I welcome you back to this online series on aircraft performance. So in the last class, we discussed basics of takeoff performance. In today's class, we will be discussing more concepts regarding to takeoff. Let's begin. So in the last class, we understood that the total takeoff procedure involved the aircraft that is on ground plus for some distance the aircraft that will be in air. The distance where the aircraft would be on ground, I call it as the ground roll, and the distance when the aircraft is airborne, that is called as air roll. Right? So now let's consider the first part. Right? In ground roll, what all the different velocities are there? Assume that the aircraft is stationary and the pilot gets the signal from the air traffic control to start the takeoff procedure. So the pilot pushes the throttle to its full power, releases the brake, and the aircraft starts to accelerate. Now, let's give numbers here. Let's say the aircraft accelerates from 0 to 100 km per hour. Let's say 100 km per hour is the stalling velocity of the aircraft. So what do you mean by stalling velocity? It is the velocity at which the aircraft generates maximum coefficient of lift. Right? Or in other words, it is the minimum velocity of the aircraft which can generate positive lift. Right? That is the minimum velocity with which the aircraft can fly. So that is stalling velocity. At this point, the aircraft, I can take it off the ground, but I won't. What are the reasons? Because stalling velocity is the very edgy point. Right? If something happens, if there is a headwind and there is a reduction in velocity, the velocity drops even by, let's say, 10 km per hour. The aircraft is not going to take off, it is going to come and hit the ground again. It's a very risky point. So as a pilot, I decide not to take off the aircraft at this point. Then I move on to the next velocity. Let's call this velocity as, let's say 150 km per hour. This is the velocity beyond which the rudder of the aircraft is under my control. Which means I can control the directional motion of this aircraft beyond this velocity. Right? Beyond 150, I can control the aircraft. Okay, fine. If there occurs an engine failure in a multi-engined aircraft, I can control the aircraft without any difficulty and I can bring the aircraft to halt when beyond VMCG. Right? That is why it is called as minimum control speed on ground. Getting the point? So I reach this point and I can tell to myself that okay, now I have reached a point or velocity at which I can control the aircraft even if the engine fails. Now I can take off at this point, but I don't, because when the aircraft is on ground, I can easily control it. But when the aircraft is in air, it is very difficult to control. So I have not reached that point where I can control the aircraft when it is in air. Right? So I do not take off at 150, rather than I will go to 200, where I call that velocity as VMCA. That is the minimum speed required to control the aircraft in air. And then it moved on to VMCG, which is 150 km per hour. Then now it is a new velocity, that is 200 km per hour, where I can control the aircraft even when it is in air. So now I have reached a confidence level where I can tell that when the aircraft is stalling speed that I have covered, I can control the aircraft on ground. Also, I can control the aircraft when it is in air. Right? So, can I take off the aircraft now? The answer is no. Because there are still few points I have to cover. So again, all these velocities what we have discussed till now are all just reference velocities. They are not the actual velocities where I'm going to take off. Remember this. That is just reference, okay? If the speed exceeds 100 km per hour, it means that we have exceeded the stalling velocity. If it exceeds 150 km per hour, it means that, okay, I got the control over the rudder to control the aircraft even if the one engine is failed. And if it moves beyond 200 or 250, that means that I can control the aircraft even in air with one engine not operating. Right, so these are all reference velocities. I am not decided to take off the aircraft till the decision speed. Right, so I reach, let's say 300 km per hour. I call that velocity as V1. V1 is the decision speed where the pilot has to decide finally to take off the aircraft or not. Right? If the pilot decides to take off the aircraft, then the distance required on the runway is sufficient to do a successful takeoff. The pilot decides to not to take off, then the runway distance available is sufficient to stop the aircraft. Right? This point is very important. That is why it is called as the decision speed. The conditions or the possibilities available with the pilot is, if the engine fails before V1 velocity, let's say if V1 is 350 km per hour, if the engine fails at 300 km per hour when the aircraft is accelerating on the runway, the pilot can stop the aircraft, he can abort the takeoff. But if the engine fails beyond 350 km per hour or beyond the decision velocity V1, the pilot can take off the aircraft with one engine not operating. Clear? These are all very interesting concepts. I hope you are enjoying this. I will try to reach another velocity, which is called as the takeoff rotational speed, where the pilot is going to deflect the elevator to increase the angle of attack. Angle of attack is increased, coefficient of lift is increased. Coefficient of lift is increased for the given velocity, the aircraft lift is going to increase. Aircraft lift increases means the aircraft is ready to leave the ground. Even at this point, I decide not to take off. You know the reason? I deflect the elevator, the aircraft angle of attack is increased. But imagine if it goes to, let's say 13 degrees, 14 degrees, where the tail touches the runway, it is called as tail drag. So it causes damage to the airframe. So I don't want that. So in order to avoid that, I will move on to next velocity, that is the minimum unstick speed. So in this minimum unstick speed, let's say it is around 400 km per hour. With this speed, I have overcome the problem of the tail drag. Right? I have avoided that problem. I have increased the velocity to the next value, that is VLO, velocity of liftoff. Now this is the final velocity where I have overcome the problem of stalling. I have overcome the problem of controlling the aircraft when it is on ground. Also, I have overcome the problem of controlling the aircraft when it is in air. Also, I have managed to take off the aircraft beyond V1. Then I managed to not drag the tail on the runway. Then I have continued to increase the angle of attack without the tail touching the runway. And finally, I have reached the velocity of takeoff where it is fully safe for both the aircraft as well as passengers to take off at this point. Now this is the velocity at which the airplane is actually going to leave the ground. So this distance, the distance from where the aircraft velocity is 0 and up to the liftoff velocity, this total distance is called as the ground roll. Right? So we will try to derive this expression, and before moving on to deriving the expression for the ground roll, let's understand the balanced field length. Right? So what is balanced field length? It is the shortest field length at which a balanced field takeoff can be performed, right? So what do you mean by balanced field takeoff? Let's say the aircraft approaches V1 and it keeps on accelerating. Now, if there is an engine failure, the distance available to take off and go away from the obstacle is same as the distance available to stop the aircraft. This is called as balanced field length. So it is the total distance from rest to the clearing of obstacle. The total entire distance is called as the balanced field length. So let's derive an expression for the liftoff distance or the ground roll. I can write the net effective force on an aircraft during the takeoff as F is equal to thrust minus the net drag force, which includes the drag and the frictional force. This net force, I assume it as constant. Then the liftoff distance is given by S is equal to V square M by 2 into F. This is the same expression what we derived. And for liftoff, I am going to substitute the value of F, which is the thrust minus drag plus the frictional force. We will try to include the margin of safety of 20%, right? So with this, the liftoff velocity is 20% more than the stalling velocity. So rather than giving the stalling velocity, I'll give 20% more than the stalling velocity. That will help me in any adverse condition, right? So how to get this stalling velocity? Using the lift equation, that is L is equal to half rho V square S into CL. So if V is the minimum velocity of the aircraft, then CL should be maximum, right? So from there, I got the expression for stalling velocity, that is under root of 2W by rho infinity S into CL max. Now substituting this value of velocity in the liftoff distance equation. So I'm going to get 1.44 W square by G into rho infinity S into CL max multiplied by thrust minus drag plus the frictional force, right? But if I observe carefully, the thrust for any aircraft during the takeoff is much greater than the sum of drag and frictional force. So comfortably I can neglect the drag and frictional force when compared to thrust force. So by neglecting these two terms, finally I get the distance for liftoff or the takeoff distance as 1.44 W square by G into rho infinity S into CL max into T, where T is the thrust required. Clear? So let's do few observations. The first observation is the takeoff distance varies directly as W square, that is the square of weight, right? And since thrust depends on density and density is inversely proportional to the takeoff distance, so as density increases, the takeoff distance reduces. So that is the case if, for example, let's take two airports, one at Switzerland and the other at Dubai. So one is extremely cold, the another one is extremely hot. So where there is cold, the density is very high. So higher the density, the runway distance required for takeoff for the same aircraft is less compared to the runway distance required for takeoff for the same aircraft at Dubai. Because there the temperature is high, the density is low. So this equation tells that if density is less, the takeoff distance required would be more. By changing the parameters, coefficient of lift maximum value and the thrust, I can change the takeoff distance. Let's say, for example, how to change coefficient of lift maximum value. One way is to deploy the high lift devices, right? The function of high lift device is to give the additional coefficient of lift required during takeoff and landing, right? That is how there are various types of high lift devices. There are leading edge flaps, trailing edge flaps, leading edge slats, slots, so many different types of high lift devices based on whether I want the higher coefficient of lift throughout the change in angle of attack, or I just want to increase the coefficient of lift maximum value. So based on the preferences, I select the type of high lift device. So based on that, coefficient of lift maximum value is going to change. And of course, thrust value I can change. That is, as a pilot, I will push it to the maximum, because higher the thrust, minimum will be the takeoff distance. Now, till now, we understood how to calculate the ground roll. Now, let's move on to the second part of the takeoff distance, that is the air roll, that is represented by SA. So, once the aircraft lifts off from the ground and until it clears the obstacle in our case is, for passenger aircraft it is 35 feet, and for military aircrafts it is 50 feet, right? Up till that point, we will calculate the distance traveled by the aircraft, and the sum of air roll and ground roll is the total takeoff distance for the aircraft. Clear? So ground roll we just calculated, air roll we will be calculating now. So consider this scenario where at this point the aircraft just left the ground, and this is the point where the aircraft is going to clear the obstacle, right? So that arc radius is given by capital R, and this dotted line is the flight path. The angle between the starting of the curve and up till it clears the obstacle, so that angle is given by theta OB. OB represents for obstacles. Understand the equation, that is the turn radius equation given by R is equal to V infinity square by G into N minus 1, right? Where N is the load factor. Now, if you don't know what is load factor, it is just the ratio of lift to weight, right? For example, for takeoff, I need the load factor to be greater than 1. Why? Because I need lift to be greater than weight for the aircraft to lift off from the ground, isn't it? Correct. So lift should be greater than weight during takeoff, right? So I need load factor greater than 1. Whereas in cruising, the load factor would be 1. Why? Because in steady level flight, lift would be equal to the weight of the aircraft. Now, using that equation, I can calculate what is the distance, that is the radius of this arc, and I will apply the trigonometric function for the angle theta OB, that is for this particular triangle. So cos of this angle theta OB is equal to adjacent by hypotenuse side. So the adjacent side is nothing but the total distance is R minus the obstacle height. I get R minus HOB, that is the adjacent, and the hypotenuse of course is R. So cos theta OB is equal to R minus HOB divided by R. Right? With this I can calculate the theta value, and from the geometry I can calculate the air roll, that is SA. If I apply sine of angle theta, I am going to get the opposite by hypotenuse. Opposite side is SA and the hypotenuse is R. So if I solve it for the SA, that is the air roll, I get R into sine theta OB. Clear? So this is the methodology involved here. First you calculate the R, then we'll move on to calculate the theta obstacle, and if we have these two values, I can calculate the air roll. In this lecture, we discussed the takeoff performance. We derived the expression for ground roll as well as for air roll. So in the next class, we will be discussing about the landing performance, right? I'll see you in the next class. Thank you very much.